I can probably have a verbal attempt at containerization at the end if anybody's interested. I guess before starting, I just want to see, does anybody here live in the Gold Coast other than me? No? All right. I mean, the area is not really known for tech, but there was actually a Digital Equipment Corporation site out near Bond University all through the 90s. It's about like 80 people working there. It does have some kind of heritage, I guess. All right, so what is Bhyve? It's kind of a strange name. It's just a small acronym of BSD and hypervisor. If you just drop away enough letters there and add an E on the end, I think it comes out as Bhyve. It was a marketing person, of course, that came up with that. So what it is a minimal hosted hypervisor. The Linux equivalent of Bhyve is KVM and QEMU. Bhyve actually encompasses all of those. And the other important difference and the reason why FreeBSD doesn't ship with KVM and QEMU is because of licensing. So the code of BSD is all 2-clause licensed, which is like the rest of the BSD system. You can use it for whatever you want without having to give back changes or anything. So maybe it's more suited for commercial companies, people that don't like GPL, basically. Bhyve has been in the FreeBSD base system since the 10.0 release in 2014. And for those who aren't FreeBSD users, the base system of FreeBSD is sort of the equivalent of a Linux distribution, except everything is built at the same time. So there's never a different version of a libc or a kernel. It all comes from the one source tree. So everything is always built in sync. So there's no kind of subversions of individual components. Just a little bit about the history of Bhyve. As time goes on, I can talk a little more about this. For a long time, I was kind of constrained by agreements with various employers. So it started out as a kind of unofficial project at NetApp in late 2010, where I was working at the time. The group I was in were kind of told that we had to get the NetApp operating system, which was based on FreeBSD, to run on top of a hypervisor. And the one that was put out as the leading contender was VMware ESX. Now that turns out that's actually owned by EMC, which is a competitor to NetApp. So certainly for some of us in the engineering group, it didn't seem like a very good idea to have a large piece of important intellectual property owned by a competitor. So what we decided to do was see if we could write a very minimal hypervisor that was just enough to run the NetApp operating system on the hardware that we were building. The one thing that allowed us to do this with a very small number of people and also outside of work hours was the fact that Intel had just released a CPU that pushed a lot of the work into hardware. And the name for that hardware is EPT, or basically second level page tables, which means that the hardware you can virtualize guest memory using CPU hardware rather than trying to do it in software. I think at the time, about 30,000 lines of KVM and Zen were dedicated to trying to emulate this in software. And it was also a very kind of difficult piece of software. So when Intel put out the Nehalem chips, all of a sudden that was done in hardware. And it made it feasible to write a hypervisor with a very small team. Unfortunately, that project never really succeeded internally to NetApp, but through some very generous management support, we were able to release the code base to FreeBSD, and that was done not too long after we'd started in May 2011. That code is actually still on the FreeBSD repository. If you have a look at it, it really doesn't do very much. It was specifically targeted at running NetApp's operating system, which was multi-CPU, but because we were able to modify the operating system, we put in a lot of paravirtualized work to get around some limitations, or basically a lot of extra work that we weren't prepared to do. So that line is just a feature set that was initially dropped off to FreeBSD. We supported up to 8 virtual CPUs. We supported X2 APIC mode, which is a mode that you can program the x86 interrupt controller that you can use MSR access, which doesn't need instruction emulation. We were able to spin up CPUs directly in 64-bit mode. Spinning a CPU up in 16-bit mode, which real hardware does, is actually kind of difficult within a Halem CPU. We did a very simple, lot of paravirtualized network and block. We used MSI interrupts for that, which is out of spec, but it turns out to be really easy. And we just had a simple POLMARD, it should be UART, not ART. But the serial chip didn't even do interrupts, it was just run in POL mode. That's actually completely useless to anybody outside of ONTAP, but since the code was there, the hope was that being in FreeBSD, somebody would pick it up and maybe do something with it. So it turned out that the people that picked it up and did something with it were the same people that wrote it, which was myself and some other people. So that code didn't get merged directly into mainline FreeBSD. It kind of lived in a side project branch. For quite a while, we kept sort of adding features to it, at least to be able to run stock FreeBSD, and also kind of not being able to work on it full-time really hurt that as well. But eventually, a number of years later, we got Bhyve to ship in FreeBSD 10.0 release. And I guess perhaps just as a result of the two-clause BSC license, that code has been picked up by some other people and has been ported to Lumos, user space on macOS, and there's an Intel hypervisor project that also uses pretty big chunks of the code. So just to talk about the features that it supports, because it kind of came along late in the hypervisor timeframe, we mandated that you could only operate on CPUs that support second-level paging. That is pretty much Intel, Nehalem, and onwards. And AMD has pretty much always supported that. I think there was only a very brief amount of time where they didn't do it. But all modern-day Intel and AMD CPUs are supported. The other feature is that it has very tight integration with FreeBSD. It's not really an external project that is just built. And also, we kind of fit in more with the Unix philosophy, and this is very similar to the kind of KVM, QEMU philosophy. We represent a virtual machine as a Unix process. A virtual CPU is a thread within that process. And guest memory is just demand-paged anonymous memory. So you want to use as much memory as you want, and it can actually be paged in and out if need be. One of the more complicated parts of implementing a hypervisor is that you have to emulate hardware. And that on its own is quite difficult because every single operating system accesses hardware devices in a different way. They access it in undocumented ways. They access it in ways that you had never thought of as a developer. So with Bhyve, we have quite a large set of device emulations, and probably what's the best about them is that they've been around for quite a long time and they've had a lot of operating systems banging on them and getting all the bugs out and getting interoperability issues sorted out. So we have, standard PCI hierarchy, network, block, USB, UART, audio, and just a bunch of kind of timers and interrupt controller emulations. For graphical output, the problem here is that FreeBSD in the base system doesn't actually have any windowing support. The Xorg distribution doesn't ship in the FreeBSD base system. So we had this chicken and egg where we want Bhyve to be in the base system, but we still want to be able to support graphics. So the way that we get around that is that we actually have a very small VNC server built into Bhyve. And that just provides a way for somebody who is running Xorg installed at a later time to install a VNC client, and then they can start up Bhyve and just use the VNC client as the GUI interface. The last feature I have there is, it actually came in from day one with the NetApp work, is PCI passthrough. So for PCI devices that have MSI interrupt support, you can actually assign it directly to a guest, and it can access the hardware without any intervention from the hypervisor. So a hypervisor really is only as useful as the number of guests that it supports. So because Bhyve has been around for a while, it's gone quite a bit beyond the initial FreeBSD only guest. So we support all types of BSD, OpenNet, Dragonfly and Free in both 32 and 64-bit mode. We can't go back too far in time. We can go back to maybe the early 2000s. Anytime before that, the devices that are supported just don't exist, and then the BSD won't boot. For Linux, it's kind of similar. We can go back to about that same time frame, and we can boot both 32 and 64-bit guests. All of those are multiprocessor as well. For Windows, it's a little bit more restrictive. We only really support 64-bit guests and only fairly recent. So for desktop versions, we start at 7, and we can go up to like a modern 10. And for server versions, we can actually boot 2K8, and we can go up to Server 2019. And that's all using UEFI as the boot ROM. There's a number of other operating systems that boot in Bhyve that may not be so important. So Illumos seems to work okay, Plan 9, and people periodically report booting other weird things that aren't really used very often. No, it doesn't boot OS2. So just in talking about a little bit about the components that make up Bhyve. So it's actually, as I mentioned earlier, it's very similar to KVM and QEMU. So there's a kernel module which handles the Intel and AMD virtualization hardware access. There's a character device which allows user space to start and stop virtual CPUs or run access or to allocate memory for guests. There's a shared library which just kind of hides the direct character device interface. And then we have a process called Bhyve, which is very similar to how QEMU works, and that contains most of the device emulation, starting up threads for vCPUs, handling timers, various things like that. There's also a separate process called Bhyve control, which uses the same interface, but is just used for a different reason. So if you want to just look at counters or look at the amount of memory that's currently being used by a guest, you would use that utility. So maybe the more controversial features of Bhyve is that it's wasn't really designed for novice users. The invocation of it is quite complex, and you really have to look at it as in you're building your own PC from scratch. So you have to tell the process what the PCI slot hierarchy is and what devices are in what slots, and then also the back end that you're going to be using for those devices. There's also just some general global options like the number of vCPUs you want to give to a guest, the amount of RAM that you want to give to a guest, things like that. So other than myself, I don't think I've found anybody that really thinks it's particularly useful. It is documented in the man page that ships with a base system, but most people don't really use the utility directly. They use like a shell script front end, and there's a number of them available. I think the most popular is VM Bhyve, which is in the ports directory. And also the FreeBSD handbook, which is online. It has like a large chapter on how to configure it using some of those utilities. And just as an example of what this may look like, here's an example for running Windows. So I can probably just go through those lines. The number of CPUs allocated here is 2. That's just the -C. Then underneath that, the -S parameters are basically the PCI slots or the slot numbers that are having devices attached to them. So on PCI slot 3, there's an AHCI CD-ROM device. Also on slot 5, I put the Windows install CD on slot 3. The slot 5 CD has the Red Hat VirtIO drivers that I'll be using to install for networking on Windows. In slot 11, we have the virtual frame buffer device, and then there's a number of parameters for that which are associated with VNC. So basically, that's a VNC server configuration. We're running it on the default port of 5900. The frame buffer has it's 1280 by 720, and Bhyve is actually going to wait. It won't start executing until somebody has connected in on VNC, so you get to see the entire boot process. We have an XHCI controller on PCI slot 12, and that's attached to a tablet device, which will actually come in via the VNC server. On PCI slot 18, we have a VirtIO.net device, and that's attached as a backend to the BSD tap device, which is a way to just pass Ethernet frames in and out of user space. On slot 20, we have a NVMe drive, and that's going to be the Windows install. So I've just created a file called win10.image, and I'm going to put the install onto that. Slot 31 is the PCI to ISA bridge device, which is present on all hardware. And the -L parameter is actually an LPC device. So on a real PC, the BIOS or the BIOS flash is actually on the PCI ISA bridge. So we call that boot ROM, and then I've just attached a UEFI image to that, which is going to boot Windows. And the last two parameters there, I've given this virtual machine 2 gig of RAM. The -H parameter is instructing Bhyve to exit on a halt instruction so that we can idle CPUs correctly. And the -W is just another miscellaneous option, which is ignore unimplemented MSRs. So if the guest does an MSR read or write for an MSR that we don't know about, we just return 0 or just ignore it, which Windows does all the time. So just a quick talk about what some future work for Bhyve might be. This isn't really in any order. If anything, it's just a bunch of missing features. So currently, Bhyve only supports x86, Intel, and AMD. Other architectures actually have hardware virtualization. So in particular, ARM v8, there's already a patch set for Bhyve for that. Our Power 9 has a pretty large set of hardware virtualization features. And as mentioned in a talk the other day, RISC-V now has a hypervisor specification. So somebody could pick that up and add that to Bhyve. Currently, it only supports, Bhyve doesn't expose virtualization to a guest. That's a feature called nested virtualization. That's probably most useful for hypervisor developers. But Windows in particular is actually using it for built-in functionality. So there's a lot of security features in Windows that want to run processes embedded inside a hypervisor just for an additional layer of isolation. Unfortunately, there's not really any hardware support for doing that. So it's kind of a large software project to get that going. Another feature is to allow a guest direct access to the host file system. So you can do that today using NFS, but it's a little inconvenient. You kind of have to do configuration on both sides. There's at least 2 ways to do that. So there's a VirtIO device that exposes the Plan 9FS file system, just passing direct packets across in a ring buffer in memory. So Linux supports that. It's not really POSIX compliant, but it's probably useful for a lot of things. And just recently, there's a new VirtIO specification called VirtIO-FS, which is designed to try to fix some of the problems in Plan 9. But basically, when you do this, it's equivalent to an NFS mount without having to do any configuration other than just in the hypervisor. The next one is GPU pass-through. So currently, Bhyve can do PCI pass-through, but passing through GPUs involves a little more extra work. We basically have to execute the ROM of the GPUs when a guest starts up. Intel has a feature called vGPU, I think. It's designed to partition an Intel desktop GPU into smaller pieces, and then you can actually assign those directly to VM guests. That actually involves a bunch of DRM code and also some operating system work on context switching. So there's a fair bit of work for that. Similar with USB, we can actually directly pass through an entire XHCI controller, but often you don't want to do that. You may just want to pass through an individual USB device. So FreeBSD already has a way to allow user space access to USB devices, which is the Tue Jan driver. So it would be kind of nice if we could just get an individual Tue Jan device and pass that through and make it look like it's attached to a USB controller. And the last one I have here is maybe the largest by a couple of orders of magnitude, and that would be live migration of guests, similar to what VMware can do, where basically you can just get a guest while it's running and actually transfer it to another machine with very little downtime. But I'm not sure if anyone's really looking at that. All right, so that's pretty much all I had. It was just a quick slide set. So if anybody wanted to throw out any questions. Yes?
Are there any plans to, so I know you kind of dodged the container
Oh, yeah.
at the very beginning. Are there any plans to do something similar to what Amazon and Google are doing with the likes of Firecracker and gvisor, where it's adding hypervisor pieces to container pieces and making a complete pig's ear of things?
So I don't know of anybody doing it. I mean, the pieces are all there. So, you know, we have a hypervisor that can run Linux. Firecracker is really not vastly different than Bhyve. It's probably about the same size in terms of code. We can boot Linux kernels directly. The pieces that are needed are sort of external. So it's more like the client and infrastructure tools. So an example would be for Docker. So you can get a Docker client to run on FreeBSD, and you could actually start a Linux guest, and you could run a Docker server inside a Linux guest. But I think you'd actually want something more. So what I mentioned about the host file system access, it'd be nice if the orchestration tool could create the container stacking external to the guest, and then the guest could access that through file system access rather than creating block devices, because you could keep the base container images around, you know, between guest invocations. So I think it's technically very doable on FreeBSD, but we seem to be lacking in people with the motivation to, you know, modify the existing tools. As an example, I think the Docker port on FreeBSD hasn't been buildable for about 9 months. There just doesn't seem to be a lot of interest in it.
I was wondering if you could tell us some war stories when you were first developing Bhyve at NetApp, some of the challenges you had and how hard they were to overcome, and how you eventually got there.
Right. So I think maybe an example is spinning up multiple processors. So when Intel first put out the Nehalem, it couldn't run 16-bit guests. You had to have paging enabled. So you had to, the minimum guest you could run was 32-bit with paging. But on x86, that's kind of a long way into the boot of a guest. We're able to avoid it on a single CPU because in a virtual machine, you can jump directly into 64-bit. That's how the FreeBSD loader works. So we're able to run the kernel because the kernel is always 64-bit. So that part, you know, we kind of got that up and running, thought that things were going really well, but you know, no one is interested in a single CPU guest, particularly the management chain that we were trying to prove that, you know, this was a viable piece of technology. So the one place where we couldn't avoid running 16-bit code is when you run a secondary CPU. You know, basically the way the Intel architecture works is that a secondary CPU is sitting there parked in a state that it's waiting to be woken up in 16-bit mode and start running in 16-bit mode. And then the operating system itself will transition, you know, all the way up to 64-bit mode. So what existing hypervisors were doing was they had enough instruction emulation that they could run that phase in software. And then once they got to 32-bit mode with paging enabled, then they would shift over into a VTX and then continue. And they're able to do that because of the heritage of that code. Like QEMU started life as an instruction emulator, so it had everything there. But the initial version of Bhyve had 0 instruction emulation. So we're kind of faced with this problem where, we had to run this code path, for secondary processes to get to 64-bit mode. So the way we ended up doing it, because we own both parts, we own the hypervisor and the guest that it was supposed to run. So we actually modified the guest so that we could boot secondary processes directly into 64-bit mode. And it turns out that FreeBSD is kind of structured that all the early code that runs in 16-bit mode up to 64-bit mode is all written in assembler, and then it basically calls a C routine once it's in 64-bit mode. No, it isn't actually. It's ap-startup.s. It's a different set of code. So we were able to modify FreeBSD so that we just skipped that code. When it started, we changed the instruction pointer to basically go straight to where the 64-bit code was. And then, once you're there, you never go back into anything less than 64-bit code. You never call back into BIOS or anything on a 64-bit operating system. So it was kind of, we had to really think from the reverse direction. Initially it's like, oh, you have to do this, software emulation of instructions to get to this point. But if you kind of look at it backwards and go back to where you need to be, it sort of became obvious that, well, we don't really need to do that at all because we can change the guest. We can just jump straight into 64-bit mode. Yeah. So I guess it's not really a war story as in fixing a bug, but it's just, it took a while to work out how we could kind of get around that problem. Of course, the issue was once Bhyve made it into FreeBSD, we no longer had the ability to modify the guest. You're running existing binary images that assume that they're running on an Intel architecture compliant CPU. So the way that was fixed was also by Intel. So the successor to Nehalem is Westmere, and Westmere introduced a feature called unrestricted guest, which you can start up a guest without paging enabled, basically in real mode. So once you do that, you can start in 16-bit mode, and everything just works fine. At the time, Westmere, we suspected that it may be a server-only feature, but I think it's Sandy Bridge was the follow-on from Nehalem. Intel introduced that feature across the entire product line, and that was kind of a big sigh of relief because they had fixed the problem that we'd found. And really, there's only like a 6-month gap between Nehalem and Westmere, but unfortunately, Nehalem's are very cheap on eBay, so every now and then somebody will buy a Nehalem system for $20, and they'll send an email to the virtualization list saying, oh, I can't boot more than one CPU, and that's exactly that problem.
Hello.
Hi.
As an everyday user of FreeBSD as my main desktop, I would like to run virtual machines, but every time I've looked at Bhyve and what's involved, I just say, too hard basket. I just use my Linux laptop over there and run VMs on that. So what do we have already, or is there anything in the works to actually make it easier for people to use Bhyve?
So what I did mention, that there's a number of front ends to Bhyve that kind of take away a lot of the complexity that I showed in that slide. They hide all the configuration for you and just use sensible defaults. So the VM Bhyve port seems to be very popular, and it's just kind of like ZFS. It's just a command line, and it has a bunch of verbs like create, start, stop, list, things like that. There isn't really any GUI front end to that. I think you're still limited to just the command line. I guess with Bhyve, at some point there'll be a configuration file where you could inherit. So there might be sort of like Amazon, where they have a fixed set of machines. FreeBSD might ship a fixed set which has fixed configurations, and then you can just override some of the parameters. So that might make things a bit easier.
Thanks.
Hi, thanks for the talk. I have a question about GPU pass-through.
Yeah.
The way it's done on Linux and Chromebooks, is through VirGPU or Virteo GPU and running an application called Virtual Renderer on the host, and that allows you to have pretty much standard graphics stack on the guest, and you can run whatever you want as long as it supports OpenGL on the host.
Yep.
And it seems to be like similar to what you've done for other features. Is that something that you've looked into?
Yeah, so it's like a general BSD issue. So, you know, BSD has the concept of the base system, which is everything that's in the source tree, and graphics is not part of that. So the issue is if we had a VGL emulation, we can't link against anything. So we would have to provide either a loadable interface and a way to have external device models. So that's actually needed for other things. One example is the VNC server that's in Bhyve is extremely limited. It has all these problems with, you know, foreign language keyboards or different VNC clients. And one of the vendors who was shipping a product that used Bhyve, they fixed that just by getting the GPL licensed libVNC server and just dropping it in. And that like fixed everything. But you know, you can't ship that on the FreeBSD base system. So they requested like an interface where at runtime they could provide a module that came from, you know, outside of FreeBSD. So I think the VGL would be exactly that. You know, we'd have to have maybe a skeleton or even just a loadable interface, and then all the code that links against OpenGL libraries and everything would have to live outside of the source tree. So yeah, it's more of an organizational issue rather than a technical one. It turns out PCI pass-through is actually much easier just because the device is always there and there's no libraries to link against. It's just hardware, and the guest supplies all the code for that.
So I was just wondering about other architectures. Whether is anyone doing the work to make Bhyve run on, say, ARM64 or, you know, my pet processor RISC-V?
So on ARM v8, there was a Google Summer Code project, or a number of Google Summer Code projects to do that work. And there's actually patches floating around somewhere. It seems that they're kind of difficult to integrate. It involves a lot, there's still a lot of work to do to get those into the main source tree. And the other problem with ARM v8 is just virtualization is a huge moving target. You know, every iteration of the architecture keeps adding features, and then you have to support all the subsets that have been before you. So I'm hoping to not get involved with that. I mentioned Power9. I actually have a Talos Blackbird system, so I'm hoping to do some work with that. RISC-V, I guess it's just a very new thing. You know, the hypervisor spec, I guess, is still yet to be frozen.
It's frozen as of, well, it's very nearly frozen.
All right. Well, looks like you're putting your hand up for that. So,
I know.
very good.
Thank you.
All right. I think, does anybody have any more questions? Okay. Thanks very much.